ch14, chapter 14, phasors and complex numbers continued. Section 9 is mathematical operations with complex numbers. So what is J? J is an imaginary number. Is it really imaginary? No. It exists, but that's what it ended up getting called. It's an imaginary number. It's the square root of -1. So it has some special properties. J squared equals -1. And I divided by j ends up equaling -j. So I divided by -j would end up equaling +j. And you can do some manipulations with that property. The complex conjugate, if you're given a complex number x plus jy, the conjugate of c of that number is x minus jy. So you just flip the sign of your second component, your reactive or imaginary component. The polar form, c equals z angle of theta. The conjugate of c equals z angle of negative theta. So you just change the sign of your angle, whatever number that ends up being. The reciprocal 1 over c is equal to 1 over x plus jy, or 1 over c equals 1 divided by z with the same theta angle. So, and they actually show that like this. That angle ends up being, it's 1 over z to the negative, like that. And addition of complex numbers, you add the x's and plus j and add the y's. So whatever signs of your numbers you end up having, this is c1 plus c2 equals plus or minus x1 plus or minus x2 plus j, and then the plus or minus y1 plus or minus y2. So in again, rectangular form lends itself much better to addition. You can't just add when it's in the polar form, like add the z's together and the thetas together. That's a common trap. Don't do that. Subtraction, same thing. It's much better to do it in rectangular. This is how you do it. Same way. You just subtract the two numbers. You would put if you're C1 minus C2, so it's going to be a negative here and a negative here. Multiplication in rectangular form, which again doesn't lend itself so well. You have to use the FOIL method. So if C1 equaled x1 plus jy1 and C2 equaled x2 plus jy2, then C1 times C2 would be x1 times x2 minus, this would be y1 times y2 plus j of x1, or y1 times x2, and then plus x1 times x2. You have to use the FOIL method. Actually, I think that shouldn't be a negative in there. That should be a positive. Y1 times y2 in there. That might be a typo in the book. And then division, it gets really complicated and hairy. Then this is the formula for it. It's ugly. I don't recommend it. When you're going to do multiplication or division, I would convert to polar form first and then do the math, and then you can convert the answer back to rectangular if that's what is being required of you. It's much simpler. C1 times C2 equals Z1 times Z2, and then you just add the angles together. And then division, C1 divided by C2, you just take Z1 divided by Z2, and then in the numerator, it's theta 1 and then the theta that was in the denominator becomes negative, so you end up subtracting theta 2. And then lastly, we're talking about phasors. What is a phasor? A phasor is a complex number that has magnitude and direction that represents sinusoidal voltage or current in the frequency domain that makes calculations easier on sinusoids. So, like I've been saying through these notes, if you are given a a sinusoid, small v or small I, lowercase, I mean, that has a max value of v sub m, kind of like what we were talking about up here. If you have one of these two sinusoids, okay, and they're actually going to have, they will have a phase angle too. Okay, so the two sinusoids look like this. So in order to convert them into phasors, you take the v sub m, which is your amplitude of, if you're converting a voltage, you would take the amplitude of that sinusoidal voltage, and that ends up equaling to square root of 2 times V R RMS. Okay, so if the sinusoid looks like this, the way to convert it to a phasor, and that's phasor in the book is shown as boldface type. Um, you might get like a bar if you're drawing it on paper. You either draw a bar or a bar with an arrow over top of it showing it's a vector, and that's VRMS with the same phase angle as this phase angle. If that's negative, then this is going to be negative. It's the same number. And then an example of a sinusoid with amperage current would be I times I sub m times the sine of omega t plus theta. And again, this is going to be, like theta I or something like that. So I fix this up real quick. If your sinusoid is a voltage V equals V sub m times sine of omega t plus theta V, then this is what the phasor form looks like. So you have to take that amplitude and divide it by the square root of 2 to get the VRMS value. And then your theta V ends up equaling the same number here. And then with the current, I, small I, equals I sub m times sine of omega t plus theta I. Your phasor form would be I sub m divided by the square root of 2, which is the RMS value, uh, and your phase angle would be theta sub I, which is this number. And lastly, someone asked me at some point, why use complex numbers to represent amplitude and phase of AC waveforms? Why is it that in AC circuits sine waves are represented as a complex number in polar form? I don't logically understand from a physical perspective why there's an imaginary part at all. Is it purely from a mathematical point of view to make the analysis of circuits easier? The answer is yes. Using complex mathematics for describing sinusoidal circuits has no direct physical relevance. It is just to make analyses easier. So when you have a linear circuit and stimulate it with only one frequency, remember this is singular frequencies. This isn't multiple frequencies. That omega or F is not going to change. Wherever you look, you always find the very same frequency. Only the amplitude and phase of the wave you measure change. What you do then is say, well, let's forget frequency. If you keep track of the amplitude and phase of the voltages or currents around the circuit, it will be more than enough. How do you do that? So you use vectors. A vector has an amplitude that is the length and a phase that is the angle it forms with the x-axis. Counterclockwise direction is positive, so as it goes around from the zero angle, it becomes positive. Okay, vectors are cool, but is anything cooler? And why do we need to use the imaginary unit? Making calculations with vectors is quite a pain, a notation pain. So if you had a vector of 2, 3, and 1, 7, and you wanted to add them together, it would look like this. Okay, so you're adding the 2 plus the 1 to get the 3, 3 plus the 7 to get the 10. That's an addition alone. Not only a notation problem, but if we choose another base of r squared, things may be better, and the base happens to exist, but requires the imaginary unit j. So this previous mess becomes this, where we're adding the 2 plus 3j, or I like to put the j in front, j3, it doesn't matter. And then I plus j7 ends up equaling 3 plus 10j. It's much easier. What is the imaginary vector in common with a voltage? Try to imagine a Gauss plane. The x-axis is the real axis, the y-axis the imaginary one. So if you could see this, this is a voltage, okay, and this is the amplitude right here. They kind of have it turned on its side as we normally look. This vertical axis is the time, is elapsed time. So it's showing how a sinusoid gets converted graphically into a vector. All right. So this is in the frequency domain and this is in the time domain. And this is called a phasor. So this is kind of like showing you, the book shows you different pictures and different phases of this, but it doesn't show you obviously like a video. And I just thought that it was an easier way to understand what we're doing. We're converting a voltage or a current into a phasor in order to make the calculations easier of it. So the angular speed W or omega corresponds to the desired frequency. That's radians per second, like how fast it's going around this circle. So that's kind of showing you how this works. And then what they're showing you here is a couple different voltages, actually three, and possibly there's a current mixed in there. And then this is the relationship between the three of them. So this is how, if you wanted to add, sum them together, this is what those three would look like. You have Y, Y1, Y2, and Y. So it's just something to think about when we're talking about phasors. This is kind of how it works. So Ohm's law holds with phasors and complex impedances. So we can continue to use Ohm's law and Kirchhoff's laws, Kirchhoff's current law and voltage law, and be able to solve these AC circuits using phasors.